You are familiar now with some curious drag phenomena. You have seen that at low air speeds, a smooth ball has less drag, while at higher air speeds, a roughened ball has less drag. You have seen that streamlining reduces drag in air, while it increases drag in glycerin. You have seen that in a certain range of speed, the drag of a sphere actually decreases while the speed increases. At this stage, matters look pretty complicated, but actually, there is order and logic in all you have seen. There is only one way to discover this order and logic, and that is by thinking in terms of the fundamental concepts and principles of fluid mechanics. The first concept is that of a continuous fluid. We know that matter is really made up of billions and trillions of molecules separated by empty space. But on a scale of size which is very large compared with molecular distance, matter appears to be continuous and unstructured. Rather than think of all the individual molecules of the real fluid, therefore, it is convenient to replace the real fluid by what we call a physical model. This model has neither molecules nor structure. It is continuous, and it has certain average properties which represent the statistical behavior of the countless molecules of the real fluid. One such property is the density. Let us think of a very small lump of fluid, smaller even than this droplet, which nevertheless contains many molecules. The average density is defined as the total mass of all the molecules of the lump to the total volume of all the molecules with their surrounding space. Density is mass divided by volume. But each lump or particle of fluid may have different properties. For example, not all particles have the same motion, as you can see by looking at the flow in a sink. To make it easier to understand such complex motions, we imagine the entire body of fluid to be subdivided into many small fluid particles, each having its own trajectory and history. Each and every such fluid particle obeys Newton's law of motion. Consequently, we can learn a great deal about the flow as a whole by focusing our attention to begin with on the dynamics of some typical fluid particle. Suppose that a tiny cube of water in the jet were dyed a bright color, so we could follow it easily. Let us isolate this cube mentally from the surrounding water, and then let us consider the forces acting on it, and how these forces influence its motion as it flows from the faucet, swirls in the sink, and departs down the drain. Let this block represent, on an enormously magnified scale, our fluid particle. While many different kinds of forces may act on this particle, they may all be put into two categories: body forces and surface forces. Body forces act at a distance: gravitational, electrical, and so on. They act on the bulk of the material, hence the word body. If this cube were a particle of water in a quiet reservoir, it would be pulled downwards by the force of gravity. But the particle is motionless, so some other force must be present to counterbalance the weight. This other force is called the surface force. While body forces act at a distance, surface forces act by direct contact between the particle and the surrounding medium. And as the name implies, surface forces are exerted directly on the six surfaces or faces of the cube by the surrounding fluid with which it is in actual contact. On each face of the cube, equal and opposite forces are mutually exerted between the fluid inside the cube and the fluid outside. Let us look at one of the faces of our particle. The greater the surface area, the greater the surface force. And so it is convenient to think in terms of the force per unit area. This ratio of force to area is called the stress. For instance, if we push with 5,000 dynes on this face having an area of 50 square centimeters, the average stress, or pressure, is 100 dynes per square centimeter. The distributed nature of the stress is indicated by these arrows all over the surface. Suppose now that we push on the opposite face with 5,000 dynes. Then there is no net force to accelerate the particle. And so the amount of pressure acting on any one face is in itself unimportant to the dynamics of the particle. But now, suppose that we push on the second face with a force of 7,000 dynes. Then there is a net pressure force to accelerate the particle. So it is differences in pressure that count. The greater the pressure difference over a given distance, the greater is the net pressure force per unit volume of fluid. This rate of pressure change with distance is called the pressure gradient. Thinking again of our cube as the particle in a stagnant tank, we see that the weight can be supported if the pressure on the lower face is larger than the pressure on the upper face. The right-hand side of this U-tube is open to the atmosphere. Let us create a higher pressure on the left-hand side. Now we have equilibrium, and we see that the weight of the unbalanced column of liquid is supported by the difference between the high pressure at the bottom and atmospheric pressure at the top. Now suppose that the pressure difference is applied in a horizontal direction. Low pressure here, high pressure here. Gravity acts downward, and for Newton's equation of motion, therefore, it produces a horizontal acceleration. This arrow represents the acceleration. In this horizontal tube, we have a colored slug of liquid with atmospheric pressure at the open end and, for the moment, atmospheric pressure at the other end. Now watch. Force equals mass times acceleration. So far, we have considered only stresses normal to the surfaces of the fluid particle. Moreover, we have thought of the fluid particle as being rigid, like this block, so that it could be displaced and turned, but not deformed. Actually, fluid particles can and do undergo great changes in shape, even more easily than this block of foam rubber. Like the foam rubber, fluid particles resist deformation. But while the resistance of a solid depends on the amount of deformation, the resistance of a fluid depends on the rate of deformation. The fluid property, which represents the magnitude of this resistance, is called viscosity. Some fluids, like water, have a comparatively small viscosity, while other fluids, like corn syrup, have a comparatively large viscosity. To be more precise about viscosity, suppose that an initially square piece of fluid undergoes a certain amount of shear deformation, as measured by this angle. Then the viscous resistance appears in the form of tangential or shear stresses required to produce this shear deformation at a certain rate. In fact, we define the viscosity as the ratio of the shear stress to the rate of shear deformation. Viscosity is shear stress divided by rate of shear deformation. There is one very important additional fact you need to know about viscosity, and that is that the fluid immediately adjacent to a solid surface cannot slip relative to the surface. What is more, the particular material of the surface, wood, metal, glass, plastic, cannot in any way alter the viscous behavior of the fluid. This liquid is glycerin. I am loading the marking pen with colored glycerin. The fluid immediately adjacent to the surface of the cylinder moves with the surface. It does not slip. Because of viscosity, the fluid farther from the cylinder also moves, but at lesser speeds as the distance from the cylinder increases. Let's see what this change of speed with distance does to a fluid particle which is initially square. It causes a shearing deformation. But because of viscosity, each fluid particle resists being deformed. And so we have to apply a torque to overcome all this resistance. Here is an instrument, a viscometer, based on this principle. An electric motor rotates a cylinder in the fluid at a known speed. The torque required to rotate the cylinder is measured by a spring and is read on this scale. From the speed and the torque and the dimensions, we can work out the shear stress and the rate of shear deformation, and in that way get the viscosity. Here is another interesting fact. The frictional resistance between a solid and a solid depends on the normal pressure of contact. But in a fluid, the frictional resistance is almost totally independent of the pressure. It depends almost solely on the rate of change of shape of the fluid particles. Now we are ready to come back and think about how all the forces we have been discussing affect the motion of the fluid. First of all, it turns out that we need not consider gravity at all. In our experiments, the terminal speed experiments, the wind tunnel experiments, gravity in the fluid produced a buoyancy force which decreased the apparent weight of the objects. But we measured only the net weights, and so the circumstances of our experiments were such that gravity was automatically compensated for. And the other body forces, electrical, magnetic, were not present in our experiments. This leaves us only with the surface forces, that is, pressure forces and viscous forces. Now, the way in which these two forces control the motion of a fluid particle is governed by Newton's law of motion. If we add vectorially the net pressure force with the net viscous force, we get a resultant force through the parallelogram construction. This resultant force is equal to the product of the particle mass with its acceleration, or for a particle of unit mass, it is equal to the acceleration itself. Now, this instantaneous acceleration controls the motion on the next little bit of particle trajectory, and so on for successive bits of the trajectory. Incidentally, the instantaneous direction of the particle motion need not coincide with the direction of the acceleration vector, nor for that matter need it coincide with the direction of either of the two force vectors. Here is a sketch showing the parallelogram of forces, and here is Newton's equation. Net pressure force plus net viscous force equals the product of mass with acceleration. For short, this mass acceleration product is often called the inertial force. We need not concern ourselves with the mathematics of fluid flow because we can understand a great deal merely by grasping the notion of viscous forces and inertial forces. The explanation of many diverse and puzzling fluid flow phenomena hinges crucially on the realization that in different experimental situations, these three quantities are of different relative importance. For example, suppose that we had a fluid of very small viscosity. Then the viscous forces would be very small compared with the inertial forces. For many practical purposes, then, we might entirely neglect the viscous forces, thus leaving us with a simple balance between the net pressure force and the inertial force. Here is Newton's equation for fluids of very small viscosity, with the viscous forces neglected altogether. We have the balance between the pressure force and the inertial force. And in the vector diagram, the vectors for these two forces must coincide. This is for the case of fluids of very small viscosity. Now let's look at the other limit, fluids of very large viscosity. Now, the viscous forces are so large that they overwhelm the inertial forces. And for practical purposes, the inertial forces may now be neglected, leaving a balance between the pressure force and the viscous force. In the vector diagram, the vectors for these two forces must now be equal and opposite. By thinking about these two extreme cases, we realize that the type of flow may be categorized in terms of the relative importance of the viscous force and the inertial force. Viscous force, inertial force. Viscous force, inertial force. Perhaps in terms of the ratio of the two. Let's look into this. Here are several objects of different size, but they are all of the same shape, and so we say that they are geometrically similar. Scale models of airplanes and ships are geometrically similar to the full-scale craft. Imagine that we carry out a series of drag experiments on objects of this specific shape. In each experiment, the particular object used may be identified by a single dimension representing its size, say its length. In each experiment, we might have a different speed of the flow. And in the different experiments, we might use different fluids. For example, air, water, oil, and so on. We have seen that the important mechanical properties of the fluids are the density and the viscosity. Here are the values of these two properties for air and water at the temperature in this laboratory. In the different experiments, the magnitudes of length and speed may vary over an enormous range, just as the density and the viscosity do. All the experiments of the series would appear to be very different from each other, and in general they are unrelated. But consider a special situation. Suppose that in two of the experiments, the several quantities in Newton's force balance bear the same ratio to each other. Then those experiments are dynamically similar. And from the point of view of mechanics, they are in a sense identical experiments. Now, different experiments are dynamically similar only if a special combination of these quantities is the same. That combination is the density times the speed times the length, all divided by the viscosity. This ratio is called the Reynolds number, after the engineer-scientist Osborne Reynolds, who gave us the first clue to this idea about 80 years ago. Here are two geometrically similar objects, both spheres. This plastic ball with a diameter of 0.60 centimeters. And this is a helium-filled balloon with a diameter of 100 centimeters. By adding various weights to the balloon, we carried out a series of experiments, in each of which the terminal speed of ascent had a different value. In one of these experiments, the terminal speed was 5.4 centimeters per second. And you recall that the diameter is 100 centimeters. We dropped the plastic ball in water and measured its terminal speed of descent. It was 55 centimeters per second. And you recall that the diameter was 0.60 centimeters. Now we may combine these numbers for the density, the speed, the length, and the viscosity, according to the Reynolds number formula. For the helium balloon rising in air, we found that the Reynolds number was 36, while for the plastic ball falling in water, the Reynolds number was 37. You can see that for the experiments we selected, the Reynolds numbers differed by only a few percent. So while these two experiments, one in a gas, one in a liquid, appear very different to the eye, they are empirically similar. And as you will see later, from a measurement of the drag of the plastic ball in water, this similarity enables us to predict the drag of the helium balloon in air. This idea of dynamic similarity is the very basis of wind tunnel testing and other forms of model testing. It is the key by means of which we can predict, from measurements made in the wind tunnel on a model airplane, the forces which the real airplane will experience. The Reynolds number shows us something else, for it is a measure of the ratio of the inertial forces to the viscous forces in the force balance. Very, very low Reynolds number, for example, means that the viscous forces are so large compared with the inertial forces that the inertial forces may be neglected. We then have a balance between the net pressure force pushing on the fluid and the net viscous force resisting the deformation. Very, very high Reynolds number, on the other hand, means that the viscous forces are so small compared with the inertial forces that the viscous forces may be neglected. We then have a balance between the pressure force pushing the fluid and the inertial resistance to acceleration. To summarize, very, very low Reynolds number means highly viscous behavior. Very, very high Reynolds number means only slightly viscous behavior. We've talked a great deal about the forces and the motions and how they are related for typical fluid particles. But now how about the forces acting on an object, moving through a fluid or stationary in a moving stream of fluid? The important idea here is that these forces are exerted on the surface of the object by those fluid particles which are in immediate contact with the surface. On every element of surface area, the adjacent fluid particle exerts a normal force and a tangential force. In general, these two forces have components in the direction of the oncoming flow. Let us look first at the frictional forces. You can see that over most of this body, the tangential forces are nearly parallel to the direction of the oncoming flow. Thus, they contribute considerable frictional drag. Now let's look at the pressure forces. At this point near the nose, the pressure force normal to the surface incorporates a positive drag component. At the shoulder, the pressure force has zero drag component, while here near the tail, the pressure force has negative drag components. That is, the horizontal component of the pressure force actually thrusts the object against the flow. Adding up all such components for all elements of the body's surface, we get two contributions to the total drag: pressure drag and friction drag. Friction drag is always present because all fluids have some viscosity, but the pressure drag may be either very large or it might be quite negligible. Which it is depends on the difference between the average pressure on the front half of the body and the average pressure on the rear half of the body. If the average pressure on the rear half is equal to the average pressure on the front half, then the net pressure drag is zero. But if the average pressure on the rear half is much less than the average pressure on the front half, then there is a large net pressure drag. The reason for thinking separately about these two types of drag is that they arise for different reasons, and since one or the other may predominate in different ranges of Reynolds number, it is not so surprising that there are different and distinct types of fluid behavior. Let us go back over the ground we have covered. We conceived the model of a continuous fluid, and then we focused attention on one of the many very small lumps forming the entire body of fluid. We noted that body forces and surface forces act on every such fluid particle, but that in our experiments, the body forces could be set aside, leaving only the surface forces. We resolved the surface forces into two components: pressure forces acting normal to the surface and viscous forces acting tangentially to the surface. We saw that these forces control the motion of a fluid particle through Newton's law, which relates the net pressure force on the particle and the net viscous force to the inertial resistance to acceleration. Then, by thinking about two extreme cases, fluids of very small viscosity and fluids of very large viscosity, we were led to a most useful idea, the Reynolds number, which allows us to categorize the type of flow in terms of the relative importance of viscosity. Finally, we recognize that the drag on an object like the forces on a fluid particle, could be divided into two parts, pressure drag and viscous drag. This set of ideas is a powerful tool for interpreting and explaining experimental observations.